let's study Newton's laws and free body diagrams. Newton's laws are exhibited in three very distinct laws, and we use them all the time. Whenever a magician is doing a trick where he rapidly pulls a tablecloth beneath some crystal or beautiful dishes, this is an example of the law of inertia, or Newton's first law. Whenever you push on an object and the harder you push, the more it accelerates, or the more massive it is, the slower it accelerates for the same force. This is an example of the second law. While the third law, the equal and opposite law, occurs when you have when this, for example, this girl is pushing an oar, and the oar is pushing the water, and the water is pushing back with the same force. It's equal and opposite. We're going to study FBDs. FBD is an acronym for free body diagrams. Common forces that we deal with. The first one is gravity. The weight of an object is written as Fg. So I want you to write the word weight, because whenever I refer to the weight of an object, or I say it weighs, I'm talking about Fg. And the formula is Fg is equal to mg. G on the planet of the Earth is always 9.8 meters per second squared, and it always points straight down. Think of it as the force the Earth is pulling on the object with. So this is a free body diagram of, say, a ball in a projectile that is only being acted on under the force of gravity. So you just have Fg pointing straight down. The normal force is a reaction force. Whenever you have an object sitting on a surface, then there is going to be a normal force. Think of this as the force of the floor pushing back up on the object. It's always perpendicular to the surface. Now, in problems, you will often see a scale reading, especially when we do elevator problems. The scale is reading the normal force. So if I say that the scale reads 600 newtons, then you know Fn, or the normal force, is equal to 600 newtons. Well, that's not working. Okay, 600 newtons. All right. More forces we deal with. What about ropes, cords, strings? Whenever you have a rope, cord, string, the force is going to act along that rope, cord, or string. We often use Ft or just T. Doesn't matter which way you write it. And then there's frictional force. The frictional force always opposes motion. And we use a number of different ways to describe friction. We'll do capital F, lowercase f, or F with a little fr. In a little bit, we're going to learn about the two different kinds of friction, the kinetic and the static friction. Whenever you have two different frictions, you do need to determine whether you're talking about the static or the not moving friction, or kinetic or moving friction. We'll discuss those more in a minute. More forces that you need to know about are spring forces. Whenever you push on a spring, you can feel the force. And the force always points in the opposite direction of compression. So if you push in on a spring, then the force is pushing you out. The spring is pushing back out. Air resistance is a special kind of friction that always opposes motion. So let's say we have someone who is in free fall here, and his force due to gravity is pointing straight down. If he's experiencing air resistance, the air resistance will point straight up. And we're going to call this FR. All right. So you need to have the steps for drawing a free body diagram very clear in your mind. The first step is to read the problem. I know this sounds fundamental, but read the problem. The second step is to identify all the forces in your problem. Some of these will be stated, some will be implied. Draw the object as a box. I don't care how creative you are or how artistic you are, every object is a box. Draw the forces as vectors. Now, all the forces need to start on the object. So the tail of the vector needs to be on your object. The length of the arrow is the magnitude, or how large your force is. And the arrow should point in the direction of the force, because forces are vectors. Now, this is a good example of how to draw a good free body diagram. You've drawn a box, okay? The forces are starting on the box and they're heading away from the box. You have arrows. If you're good, you have labeled them. So this is my applied force, normal force. I've got a block sitting on a table apparently. FG points down, and this is friction. How do I know it's friction? Because it's contact, it's right there, and the last thing I want to put in is the acceleration. I want to show the direction of my acceleration. This one's not very good because the forces aren't starting on the box. They're actually heading toward the box. Now, Newton's law in free fall. If I have an object, this poor guy is about to jump out. As soon as he is off this ledge, his weight will pull him straight down. Now he's got this fancy little parachute. He will have some air resistance pulling him up. However, I'm afraid this guy is still going to find he accelerates downward. He's not going to have a nice constant speed for quite some time. Alright, so he will have some acceleration pulling him straight down. There's no normal force. Why is there no normal force when he's midair and not sitting on a surface? Because he's midair and he's not touching a surface. As soon as he touches down and is on the ground, he'll have a normal force. Okay, let's try drawing some free body diagrams. What would it look like if I had a box sitting on the ground? Identify all your forces. Okay, you're going to have FG. Alright. You're going to have the normal force. Do you have anything else? It's sitting there. Draw the object as a box. Alright. So here's my box. Draw FG first. Always draw FG first. And then draw your normal force because it is sitting on the ground. Let me switch over here. Your FG and FN should be about the same length because the box is not moving. Now, what if I have a box on the ground being pulled horizontally with an acceleration of 2 meters per second squared? Oh. Identify your forces. Okay, I have FG, FN, and I have to have some sort of force because it's being accelerated. Draw your object as a box. Draw FG first. So I have FG going straight down. That's always the first force you draw. Second force is draw your normal force if you have one. And then I know there has to be something happening, some sort of force going to the right because it's being accelerated to the right. And I drew in my acceleration. Now, what do I do if I have a box on the ground being pulled at an angle of 30 degrees with respect to the horizontal, and it's accelerating? Okay, Identify all of your forces. All right, this one, now we're going to have an applied force at an angle. Draw in Fn and Fg first. Always draw those in. Okay, so Fg goes down, Fn goes up. And F is up at this angle. And then sketch in your acceleration. It's essential you can draw clear free body diagrams. What if I have a box being pulled vertically at a speed of 2 meters per second? All right, because it's being pulled up, let's assume it's being pulled up by a string or a cord or something. So we're going to have this tension and Fg. Draw the object as a box. Draw Fg. And let's see what it looks like. Fg, Ft. Now I have a speed of 2 meters per second. So that tells me the acceleration is 0. So out to the side, put A equals 0 and circle it. If it were accelerating up, then I would have an up arrow. If it were accelerating down, I would have a down arrow. Okay, what if I wanted to draw a free body diagram of a box on a rough surface being pulled at an angle of 30 degrees with respect to the horizontal with a speed of 2 meters per second? Now, I've told you a few things in here you may not realize. Okay, you know the forces you need to identify are Fg, Fn, and then F and theta because it's being pulled at an angle. But there's another force, and that's friction. When I use the word rough, that means friction. If I had said smooth or icy, that would mean no friction. But rough always means friction. Okay, draw your free body. Fg, Fn go first. And let's see what this looks like. Fg goes straight down. Fn goes up. It's being pulled with some force F at an angle theta. And because I use the word rough, you know there's got to be this friction going to the back, going back to the left. Now, elevator problems are really quite a bit of fun. In an elevator problem, you look at the elevator as the object, and there is no normal force unless the elevator is sitting on the ground. The only time you have a normal force in an elevator problem is when you're talking about someone standing on a scale, and we'll discuss that in a bit. Suppose an elevator is going up or down at a constant velocity. What's A? All right, well clearly A is 0. Why? Constant velocity means the acceleration is 0. The velocity is not changing. So, what are your steps? The sum of the forces, you draw your free body diagram first. Fg goes down, T goes up. You make sure you write in here that A is equal to 0. Circle it. Now, you want to use Newton's second law. Newton's second law says the sum of the forces are 0. Excuse me, Newton's first law says the sum of the forces are 0 because the object is moving at a constant velocity. Okay, this side of the equation right here is always the arrows from your free body diagram. So, let's look at this. I have T going up, so that's positive. Up is positive. Fg is going down, so that is negative. So I have T minus Fg must equal 0. Or the tension has to equal Fg, and you remember Fg is the weight, and that is equal to mg. Case 2, what do we do if the elevator is going up with an acceleration of A? Up is positive, so the acceleration points up. The free body diagram is the same. Fg goes down, T goes up, but in this case we have put in an acceleration pointing up. What does Newton's second law say? It says the sum of the forces equals ma. Once again, this summation sign over here, sum of the forces, you want to come over to your free body diagram and draw in your arrows. Any arrow you have goes on this side here. So So T goes up, FG goes down. All right, so this is the summation of the forces. And that equals the mass of your object times whatever the acceleration is. So you're going to have a mass in here times your acceleration. So I'm going to solve this. T is equal to Fg plus ma. Fg is equal to mg. So I plug that in. And I find this interesting equation, that T, the tension in the chord of the elevator, is equal to the mass times gravity plus acceleration. So this is going to wind up being larger than just the weight of my object. The third case is if the elevator is accelerating downward. Since the acceleration is pointing in the direction of the net force, the acceleration is it's going downward, it's accelerating downward, my acceleration will point downward. Now, Newton's second law says the sum of the forces equals ma, but in this case A is pointing down. Down is negative. So T points up, Fg points down. So this is equal to m times minus a. So you can just put that minus sign out front. So when I solve this, I see T is Fg minus ma. I can plug in the weight, which is equal to mg minus ma. And I see the relationship that the tension in the chord actually decreases because of the downward acceleration. Now, there is some other interesting factoids you need to know. There's only one normal force, and that's if you're standing on the bathroom scale. And then the bathroom scale reads your normal force. Let's do a problem. A man stands in an elevator that accelerates up. His mass is 50 kilograms. The scale reads 600 newtons. What is the actual weight of the man, and what's his acceleration? All right, first thing I want you to do is draw the free body. Fg goes down, Fn goes up, and his acceleration is pointing up. What givens do we have in this problem? Okay, let's look at this. His mass is 50 kilograms. The scale reads 600 newtons. All right, so his mass is 50, and the normal force is 600 newtons. Go ahead and find his weight. Weight is Fg, which is mg. So his mass is 50. Acceleration is 9.8. So he has a weight of 490 newtons. Now, sum of the forces equals ma. What forces do I have? Remember, this is my arrows. I have normal, in this case, going up, minus Fg equals ma, and then we solve it. I'm going to solve this for the acceleration by dividing the entire thing through by mass. Once I've solved it, I start plugging my numbers in. Fn is 600 newtons. Fg is 490. I already found it. And his mass is 50. This is one of my givens. And I get that his acceleration is 2.2 meters per second squared. Now let's talk a little bit about friction. Friction is a contact force. It only occurs if two objects are touching each other. It always opposes motion. It does not have to oppose acceleration, only motion. For example, if I slide a chair across the floor, as soon as it's out of my hands, it's only acting under the influence of friction. Say the object is sliding to the right. It's slowing down. Acceleration is to the left. Friction does depend upon the normal force, and there are two types of friction. Static friction, and in static friction there is no motion. The second one, and so in this case, we talk about it being less than or equal to μs times the normal force. The maximum static friction is μs times the normal force. The second type of friction is kinetic, and kinetic means friction. And kinetic is always equal to mu Fn. Now, it turns out that mu s is always greater than mu k. Let's think about this. It takes more force to get a dresser start it sliding than it does to keep it going. So that is because the static friction is greater than the kinetic friction. Let's work a problem. Suppose I have a 10 kilogram mass. All right, 10 kilograms. So we're talking about our mass here. Rests on a horizontal surface. The frictional force opposing the motion is 20 newtons. Can you guess what that is? That, of course, is friction. Okay? If a 100 Newton force, so this is just going to be some force F, is applied to the object, what will be the acceleration? All right. Draw a free body diagram. Fg goes down. Fn goes up. I didn't give you a direction, so let's just make the applied force go to the right. Friction opposes motion and goes to the left. Write out your givens. Mass is 10 kilograms. Now, if you need help figuring these out, go ahead and write them like I do in the problem. All right, 10 kilograms is mass. The frictional force is 20 newtons. The applied force is 100 newtons, and you can just call this F, that's fine. I'm looking for acceleration, so that's my unknown. What is the acceleration? Newton's second law says sum of the forces equals ma. So, go to your free body diagram. F applied is to the right. Friction is to the left, so that's negative. So F applied minus friction equals ma. Solve it. Acceleration is F applied. Looks like it's F appled minus friction divided by m. Plug your numbers in. The applied force is 100 newtons. All right. The applied force is 100. Friction is 20. And then we're going to divide that by the mass. We get 8 meters per second squared. Make sure you come in and do the numerator first. So 100 minus 20 is 80. Divide that by 10, and you get 8 meters per second squared. Let's do another one. A 100 Newton box. So when I say 100 newtons, that's got to be what? Yep, it's got to be the weight. That's Fg. Is accelerated across the floor to the right with an applied force of 20. Okay, so applied force, so we're just going to call that F. The object encounters 10 newtons of friction. All right, clearly this is going to be friction. Determine the normal force, the net force, coefficient of friction between the object and the surface, the mass, and the acceleration of the object. We're asking for a lot of stuff, but you can do this. Step 1, free body diagram. Fg goes straight down, Fn goes up. I didn't give a direction, so let's just make the applied force go to the right, friction to the left. And since it's accelerated, once again, make sure you give me the acceleration. Points this way. All right. Next, write out your givens clearly. Fg is 100 newtons. I told you it was the weight, and I gave it to you in newtons. The applied force is 20. Friction is 10. Now, the first step, find the mass. If I give you mass, find the weight. If I give you the weight, find the mass. Step 1. So, Fg is equal to mg. So, solve this from the mass. Mass is Fg divided by g, so it's 100 divided by 9.8, or 10.2 kilograms. So, right off the bat, you get one of these off your list. Next, sum of the forces in the x direction. Well, you have the actual forces. So the net force in x is going to be, let's see, applied force minus friction. So the applied force is 20, the frictional force is 10, so the net force in the x direction is 10 newtons. So when I ask for net force, right there, I've just found the net force in x. Now, when I look at the sum of the forces in x equals ma, I can go back to the beginning as I did here. You don't have to. You've already found the net force. So you could actually cheat and say F net equals ma. You'll see I use this notation or the summation. They're equivalent. They're the same thing. I don't care which one you use. So to find the acceleration, I could just use F net divided by m is equal to, let's see, I just found my net force was 10, divided by my mass, which is, what's my mass? I just found it. It's 10.2. And I would get 0.98 meters per second squared. Same answer. So, in this example, this part of the problem, I've looked for the acceleration, and I found it. So where's my acceleration? Now, I want to find the coefficient of friction. All right, I know the formula for friction. Friction is mu Fn. It's a coefficient of friction times the normal force. In this example, I haven't found it, and I need to find the normal force. So I'm going to come back up here, and I know the sum of my forces in y is 0. And I know it's 0 because it's not moving in y. I'm dragging it along. So this is my arrows. I have Fn pointing up minus Fg equals 0. So Fn equals Fg equals, I told you the weight was 100 newtons. It's the beauty of problems being drug along. So I come down here and I solve for friction. Friction is mu Fn. Solve this for mu. Mu is the frictional force divided by the normal force. So it's 10 divided by, whoops, lost it there. 10 divided by 100, or 0.1. Remember, the coefficient of friction does not have any units. All right, now, let's see if we can write an expression for the value of Fn for each of these cases. If this is just a box and it's sitting still, what does the normal force look like? If this is a box and I'm pulling up on it with some force, F pull, what will the normal force look like? In this case, I've got a box and I'm pushing down. So a good free body diagram would have the force going down like this. Figured it out? All right. In this case, the sum of the forces is 0. In all these cases, the sum of the forces is 0. The normal force minus Fg equals 0. So I'm going to come over here and solve this for the normal force. I'm solving for Fn. I've got Fn minus Fg is equal to 0. So I add Fg to both sides, and I get Fn is equal to mg. Now in this case, I'm going to sum the forces and it equals 0. But what do I have going up? I have Fn going up, and then I have this pull. And I'll never write it out like this again. F pull is going up as well, and that has to equal 0. So when I solve for the normal force, I have to add friction and subtract F pull from both sides. So I'm going to add friction, subtract F pull from both sides. So the normal force is Fg minus the force of the pull. Since friction is mu Fn, I can see the normal force is going to go down because I'm pulling up. and so the frictional force will go down. Think about that. Someone is helping you move a dresser, and they help you by lifting up a little bit. It's easier to pull it. Now let's look at this one. Sum of the forces equals 0 on this case, and I'm going to redraw the force so that it's pointing down so I can be very, very clear and correct. I'm just going to call that F push. I'm going to scribble through this because I don't want to see it. So, sum of the forces is 0. This is the arrows. What arrows do I have pointing up? Just my normal force. So, I have plus my normal force, and then minus Fg minus F push. Solving this for the normal force, I get that the normal force is equal to Fg plus the push. In this case, it's very easy to see that the frictional force is going to increase because my normal force is going to increase by the amount of that push or pull.